How's everyone doing today? Fair enough. Happy Friday. At least as far as physics is concerned, we've got a pretty light schedule for the day. So, let me hand wave at a calendar for a minute. Today is Friday, April 12th, and main thing on the agenda is Test 2, taking place next week during lab time on the 15th, the 16th, and the 17th. Like with Test 1, you can show up to this room from 1:30 to 4:30 on any one of those days and take the test then. There is no lab, there is only test. And you can show up any one of the 3 days. It doesn't have to be the one that you normally come to for lab if another day works for your schedule, and you don't have to tell me ahead of time because there's more chairs in this room. I don't have to work around the seat limitation. Class today, my plan is to go over the study materials that I have posted to Brightspace to make sure everyone knows exactly what will be on the test, and make sure you know exactly what is at your disposal to study with in the coming days. And since the test takes place during the afternoons on these 3 days, lecture on Monday and Wednesday will also be review days. My plan is everyone will finish up their test by Wednesday afternoon, and then I'll have a couple of days to grade them and get them back to you by Friday the 19th. They'll then spend the last week of class talking a little bit about electricity. We have one more lab that week that will be about electricity, and then exam territory. The test itself will be very similar to the first one in terms of formatting. It has 105 points spread among 13 questions, and it is only graded out of 100 of those points. There's just bonus points built in. There are slightly more questions than on the first one, and that's just because since test 1 we've covered a lot of different concepts. It was kind of hard to compress them down into a smaller number of questions. But to accommodate, most of these questions are shorter. Test 1 was mostly multi-parters. Test 2, those extra questions, a lot of them are simple one-liners or concept questions. Less math required per question, in my opinion, so it evens out. And I don't want the question number to concern anyone. Does that make sense? All right. As with the first test, we formatted the same way, and you will still be encouraged to bring a formula sheet and a calculator. I have formula sheets if you don't have your own copy yet. I do not have calculators if you don't have your own yet, so keep that in mind. And to help everyone studying, I plan to, that's not the right, look over the test review stuff that I have posted to Brightspace. Before that, how are you guys feeling? Do you have any questions or concerns? All right. In Brightspace, I have created a tab for Test 2, just like I did for Test 1. So Test 1 was on chapters 1 through 7, and then after that, we covered chapters, well, the numbers range from 8 through 20, and so that is what it says Test 2 will be about. Do note that we didn't cover every number between 8 and 20. We skipped a few, and a couple of those were really short. So don't let the greater number of things alarm you. It's really just in reference to everything we've covered since the first test. Again, there's individual tabs for all of those things, and you should be within each of those tabs working on the homework week to week, which is definitely like the recommendation for studying. Work on all the homework for all the relevant chapters and then do the practice stuff. But if your goal is to, if you've done all the homework, or if you just want to focus on the stuff I've made for the test, then or a projector. Within if you click on the actual tab itself, as with test 1, there is a list of concepts here. I'm going to go over this list so that you know exactly what I expect you to be able to do in reference to each of these things. And there is a list of practice questions uploaded here as its own document. I'm going to upload an answer key for this afternoon so that you'll be able to check your answers as you're working on it. If you do nothing else to study for this test, taking these practice questions is probably your best bet. The way that I make these is I make the test itself, and then I make this so that I know exactly what concepts need to be on it and how you need to use them. I do make the practice test longer and more difficult than the test itself. For example, the practice test is 16 questions as opposed to 13, and more of those questions have multiple parts on them just to make sure that you've got the concepts practiced. This is because I'd rather you make mistakes here than on the actual thing. Sound fair? Okay. Then, let's look over this concept list and make sure that you guys know everything that you should be familiar with before test day. First thing on this list, I want to acknowledge that there are concepts from within the first test list of chapters that we've been using all the way throughout the semester, and therefore they still reappear even if we didn't cover a chapter on them in 8 through 20. Those common concepts that get reused a lot include units, using units and converting units, basics of motion, and also basics about force. Doesn't matter what chapter we're on, those elements just kind of show up time and time again. So keep those in mind. They're not necessarily on the chapter list, but we used them within those chapters. Moving on through the stuff that is in chapter 8. 8 was about rotational motion, and it was kind of a long one. We try to compress most forms of rotation into that one chapter. Rotational motion itself, we described that in terms of angular displacement and angular velocity, which is the amount that something spins and how quickly something is spinning, as opposed to linear motion, where you describe how far something moves forward and how quickly something is moving forward. So it's just a different form of motion with different descriptors. But you can still convert linear motion into angular motion and vice versa, because there are loads of objects that spin and move forward at the same time, namely anything that can roll. Why did I do that? So that last blurb there is about being able to compare something's linear motion to its angular motion if it is rolling and convert them back and forth between the two. The formulas you should be able to use for that are, that's not the right page. The transformation formulas here, we didn't really use the acceleration one at all, but you should be able to use delta x equals r theta and v equals r omega. And then in the angular box, omega equals delta theta over delta t. Make sure that you're able to use those in conjunction with the classic linear versions of those formulas. Also, bless you to whoever sneezed. After talking about the basics of rotational motion, we started looking at a few specific forms of it, including how centripetal force can cause something that would normally move in a straight line to start moving in a circle around something else. All objects want to move in straight lines, and you have to literally force them to start turning into a circular pattern, and that is what the centripetal force is. It is the force that makes the object start turning, and some real existing force always has to play the role of centripetal force. What it is just kind of depends on the scenario. There's loads of times where something like a string and the tension in the string is what's supplying the centripetal force, but there's loads of time in space where gravity is what supplies the centripetal force. So be familiar with how centripetal force causes things to start turning into a circle, and that lots of different forces can play that role. Should also note we are talking about centripetal force because that's the real one, not centrifugal force, which is just a sensory phenomenon. Centripetal, with petal like a flower, that's the real one that we actually can measure and use in the class. Speaking of orbit, on eclipse day we talked about the universal law of gravitation, which I will ask about briefly. I want you to be able to utilize this formula to tell me the force of gravity between two masses based on how far apart they are. Kind of similar to on the practice lab or the examples we worked in class, I would give you all of these variables and you'd have to be able to just use the formula. This one's on the formula sheet, along with the value you have to use for uppercase G. That one's on the sheet right under the universal law of gravitation. Those are bottom right of the first page. So really I want to make sure that you can use the formula right and be able to get the correct answer out of your calculator. So note the best ways to input all the information to get the right data out. Questions so far? All right, moving on. A couple more rotational things that we talked about. For example, torque and rotational equilibrium. Torque is the idea that if you exert a force at some distance away from a fulcrum, you can cause the object to start spinning rather than start moving in a straight line. And when I say rotational equilibrium, what I'm talking about is a seesaw. In order for something to be in rotational equilibrium, all the torques acting on it have to add up to zero, like how normal equilibrium, all the forces have to add up to zero. And in lab and in class, we did seesaw questions where the torque created by this weight at this radius would have to equal the torque created by this weight at this radius. You know, two different masses either side, where do they all have to rest so that the whole system balances? When I reference torque and rotational equilibrium on the list, this is the type of question I'm talking about, and so there's one of these on the practice test. The last rotational concept that we talked about is that of rotational momentum and how that relates back to rotational velocity and also rotational inertia. And we didn't do a whole lot of math with this. So in the interest of you having the information to be able to study, what I want you to be able to do in reference to these is to describe to me what would happen in a situation where something is spinning and something changes about its rotational inertia. What I mean by that is, I will show you the practice question that references this so that you understand, so that I can try to communicate what I want you to be able to do here. This is number 6 on the practice test. A merry-go-round has all of its passengers sitting close to the center axis of rotation, and it is rotating at constant speed. So this donut here is the flat standing disc of the merry-go-round, and this is where all the people are currently concentrated, right there near the center axis. If an object's mass is close to the axis of rotation, is it easier or harder to make it spin? Easier, very good. That's what rotational inertia says. The closer something's matter is to its axis of rotation, the easier it is to make that thing spin. In reference to that, this is when I sat in a chair with these weights, spun around and pulled them in to reduce my rotational inertia, therefore making it easier to spin, and therefore I sped up. But it's also in reference to things like hammers versus swords. If the mass is closer to your hand, it's easier to make it spin versus if the mass is further away. So the first question here is, what happens to the rotational inertia, the measurement of how easy it is to make something spin or not, if all of those people leave the center of the disk and all head towards the outer edge of it instead, will it be easier or harder to make the merry-go-round spin? Harder. Very good. If all the people go to the outer edge, the mass is now further away from the axis of rotation, therefore the disk is harder to make spin. That's the rotational inertia part that I want you to be familiar with in a situation like this. Now the second part, if angular momentum is conserved, what effect will this have on the ride's rotational speed? The idea that angular inertia, keep mixing up the terms in my head that are synonyms, sorry. If rotational momentum is conserved, and rotational momentum is the concept that if something's spinning, it wants to keep spinning exactly the same way. It doesn't want to turn and it doesn't want to slow down if it can avoid it. When I was demonstrating this, I was using the bike tire and spinning it up and then hanging it, and it wouldn't fall over because its momentum wants it to keep spinning in the same axis. If the merry-go-round's angular momentum is conserved, but we have changed the rotational inertia, we've made the rotational inertia bigger and harder to make it spin, what should happen to the angular velocity of the ride? Slows down. The angular inertia is still conserved. Sorry. The angular momentum is still conserved. But if you, for example, double rotational inertia, rotational velocity gets cut in half. Kind of the same as normal momentum. Mass times velocity, inertia times angular velocity. So this type of question, conceptually, is what those blurbs on the concept list are referring to. There's a similar one on the test. And this is what I want you to be able to do in reference to these concepts. Does that sound okay? All right. That's all the rotating stuff. Any questions or objections at this point in the list? All right. Next, after the rotation chapters, we started looking at matter and pressure. We had a couple very short chapters just talking about matter itself. Main things out of those I want you to remember are the states of matter and how they are different. Solid, liquids, and gas. Solids don't flow, whereas liquids and gases do flow. Therefore, you can submerge a solid in a liquid or a gas, and that kind of then informs how fluid pressure and buoyancy work in the following chapters. So when I say states of matter, just know that there's some slight differences based on solid, liquid, or gas. Density, referring to mass per unit volume, and then the difference between volume and surface area, because some of these concepts use volume and some of them use surface area. They're not the same thing. So this section here is really just the things that we covered to then inform and help us with these concepts. So this is then the pressure section. Pressure itself, you should remember that pressure is force over surface area. So if there is a pressure acting, that means that that pressure is creating force on the surface area of whatever it's acting on. Pressure can be caused by a lot of things. It can be caused by you just pushing on something and exerting force over the area of your hand, but it's also caused by fluid pressure at depth. This is again in reference to the differences between the states of matter. Since fluids can flow, you can throw a solid into a fluid. That includes both liquids and gases. And once the solid is submerged in fluid, that fluid exerts pressure on the solid because the weight of all the fluid above that point literally weighs down on the solid in question, and therefore the pressure builds up and squeezes the object in on all sides. This happens in any liquid or gas, including water and the atmosphere. And there's a specific formula for fluid pressure at depth that I would ask you to be able to use. It is properties of matter. Wait. Ooh, oversight on my part. I don't think it's on here. My bad. Well, I need to edit this thing apparently. The formula I'm talking about is fluid pressure equals fluid density times the strength of gravity times depth. That is the formula I'm talking about. And apparently that's not actually printed on the formula sheet, so you should add it yourself manually, or alternatively, wait for me to update it over the weekend and then run off a new copy. Your choice. But this is the one that I'm talking about for fluid pressure at depth. Your depth within the fluid affects how much pressure that fluid is literally squeezing you with. So that's the formula I'm talking about. I am very sorry that's not already on there. Unless I'm missing it. Archimedes principle, Pascal's. I don't think it's there. Sorry about that. Yeah, write that down on your copy if it's not already there. Lost my train of thought. Any questions before I try to resume? Okay. Pressure at depth goes on to cause buoyant force. Basically, if something is submerged in a fluid, since pressure increases with depth, the deeper down you go in water, for example, there's more water above you, therefore there's more material squeezing in on all sides. Since the pressure is greater on the lower part of the object, there is therefore more upward pressure and force than there is downward pressure and force, and therefore there's a slight buoyant force caused by the fluid that you are submerged in. And so for the buoyant force part of this checklist, I want you to be able to use the buoyant force formula, which is on here. It's the one labeled Archimedes principle. I have to start checking that now. Be able to use that formula to calculate the buoyant force on an object, and also I want you to be able to tell me if something should float based on its density or the answer to the buoyant force equation. The rules for if something floats are basically if buoyant force upwards equals its weight downwards, it will stay where it is. If its weight downwards is bigger than buoyant force upwards, it sinks. And if buoyant force upwards is bigger than gravity downwards, it's going to rise until they equalize. So those are the rules for if something floats or not. I'm going to be able to use this answer to determine if something will float. But the tried and true method of just comparing the solid's density to that of the liquids also works just fine for determining if something will float or not. Last two pressure things up here, Pascal's principle and gas law. They're referring to specific concepts that I want you to know, but we didn't do a whole lot of math about them, so I really just want you to be familiar with the concept. And I'm going to mention now what I want you to be able to do with these. Pascal's principle is referring to the fact that a liquid cannot be compressed. If you squeeze water, you're not going to make the water any smaller. Instead, you're just going to pressurize the water. This is in reference to the scenario we looked at where there's a confined liquid inside of a reservoir, and if you push on this part of the liquid, the pressure throughout the entire liquid increases, and therefore it's going to push out on the other side as well. Again, what I want you to remember here is liquids can't be compressed. If you squeeze a liquid, that's just going to increase the pressure within the entire liquid. So that is what this blurb is referring to. Separately from that, gas law is referring to the fact that gases can be compressed. If you pressurize a gas, you can actually make that shrink, unlike liquid. Liquid won't shrink, but gas will. And so for gas law, what I want you to know is if you double the pressure on a gas, you will cut its volume in half. And if you cut the pressure in half, the volume will double. Does that sound fair? And there is a question on the practice test that references these in the way that I want you to be able to use the concepts. Feel all right for pressure stuff? All right. The last main group of things we discussed recently that'll be here is waves. As for waves themselves, recall that waves are traveling energy, traveling vibrations, and there are certain aspects of waves that we're able to measure. Amplitude is basically the size of the wave. You measure basically the disruption from baseline up to the highest point or down to the lowest point. Amplitude is not low to high, it's base to high or base to low. Crests and troughs are just the terms for the high points and the low points. Period of oscillation and frequency are inverses. Period references how many seconds it takes one wave to pass, and frequency is how many waves pass per second. Just total inverses. And lastly, wavelength is the physical length of one single wave. Those various things that we can measure about waves then go on to affect the next couple of concepts here. First of all, wave speed. Since waves travel, they have a speed. For this section, I want you to remember this formula here. Wave speed equals frequency times wavelength. And the quirk with this formula is that the speed of a given single type of wave is constant in a specific medium. If you're looking at sound, for example, you would always plug in the one speed of sound, and changing the frequency is only going to change the corresponding wavelength such that they multiply together to create the same speed. This part only changes if the wave type changes or the thing the wave is moving through changes. So if you're comparing a bunch of sound waves, you'd be reusing the speed of sound and you just have different combinations of frequency and wavelength. That's what I want you to be able to remember and use in reference to wave speed. Next, Doppler effect. This is just referring to the notion that if either the source of the wave or the observer of the wave is moving, that changes the frequency that you end up getting as a result of that. And this is in reference to the ambulance example, basically. The meow you hear as something approaches and then passes you. If two things are drawing closer together, and that can be because either of them is moving, then the waves observed between the two will be at a higher frequency than they're supposed to be. And that's the ning part. If they are moving further apart for any reason, could be either of them moving, you get a lower frequency. Lower frequency if they're moving apart, and that's the meow part of the meow. So I want you to remember that that happens, and that is the Doppler effect is the name for that happening. In case I didn't mention this out loud, bats and dolphins do this too. Basically, they know what frequency they create, and if they hear back a higher pitch, whatever the wave bounced off of is approaching the bat or dolphin. If they get back a lower frequency, whatever that bounced off of is moving away from the bat or dolphin. So, when I say Doppler effect, I'm just referring to that phenomenon. Main thing to remember is closer together, frequency rises, drawing apart, frequency drops. Okay? Okay. Wave types. There's two different categorization systems for waves, and What I want you to do here is basically know which two of these 4 vocab words apply to sound and which two of these 4 vocab words apply to light. Wave shapes. Transverse means that the vibrations are perpendicular to travel, and longitudinal means that the vibrations are parallel to travel. Sound is transverse. Well, I got that backwards already. Sound is longitudinal, light is transverse. Then, separately, there's wave structure. Waves are mechanical if they require a physical medium, and they are electromagnetic if they don't require a physical medium because they are literally made of electromagnetism. Sound is mechanical, light is electromagnetic. So, again, I want you to look at this list and be able to link. If I ask you what sound is, you link together longitudinal and mechanical. If I ask you what light is, you link together transverse and electromagnetic. Sound fair? All right. Last up, a couple more tidbits specifically about speed of sound. I mentioned that wave speed is determined by the type of wave and the medium. If you want to change the speed of sound, you basically have to change the properties of the air the sound is moving through. Speed of sound is usually 343 meters per second in room temperature air. That drops if the air gets colder and increases if the air gets hotter. So the speed of sound through air changes in the same direction as the temperature. The speed of sound also increases even more if the sound is played through water, and even more if the sound is played through solids. What does not affect the speed of sound is frequency or volume. Those have no effect on sound speed. And lastly, in reference to sound speed, note that sound velocity is still velocity, meaning it can still be displacement over time, and therefore you can use the speed of sound to figure out how far the sound will travel in a certain amount of time. This is in reference to the question where we calculated how far the thunder travels in a certain number of seconds, figure out how far away the lightning bolt was, and also echo questions where you can, time out how long it takes to hear an echo and figure out how far away the thing that it bounced off of was. The only difference between those two things is if you're hearing an echo, the sound had to double back and travel twice the distance and twice the time. That's the main difference between the thunder example and the echolocation example. How's all that sound? I'm still not intended. All right. That is the finite list of things that will be on the test. It is a varied list, but it is a finite list. And if it's not on this list, it's not on the test. The practice questions will cover the same concepts and used in similar ways, but obviously not identical ways. But it's still the best thing that you can be working on, especially if you've already finished the homework. Answer key for the practice test will go up this afternoon, so you can check your work. Lectures next week will be more review, so make sure to bring questions or email me over the weekend. Does anyone have any questions or need anything for right now? All right. Well, in that case, our options are either break 15 minutes early or I start talking about photons. Your vote. Have a good weekend, everybody. It skews a little closer to concept than the first one did, but hold on, I want to look at it before I answer. It's still, I would say maybe 50-50. Like there is still a lot of math involved, and I'm very physicist. I look at math and I see concepts. So my opinion on how much of each is there might not be what you would feel if you looked at it the same way, if you looked at the same document. loading it to lay eyes on it and try to check fast.
Like for the concept questions, like, we don't have to write a lot.
No, I've written them in such a way that the answers would be one word or a very short sentence.
Are like the questions that you have to write like the homework ones, like similar to the homework questions?
Yes, and in fact, some of the test questions are literally the
Yeah.
homework questions. Maybe tweaked very slightly, but the answers and the process would be the same. And on the homework, because I pulled most of those out of the textbook, the book usually expects full sentences. I do not.
Okay.
I write these to take you as little time as possible, because I don't want to grade long paragraphs, nor do you guys want to write them.
True.
Did you get my, lab?
Yeah.
The completed
Remind me your last name again?
one? Yes.
Yeah, I did. Oh, thank you. Yeah, I'd say 50-50 concept math, and even then, the concepts inform the math. Like if you're stuck on the math, you could write me about the concepts and I'll give you points.
Okay.
Does that answer the question?
Yeah. Thank you.
Perfect.
Thank you. Have a good weekend.
You guys too.
Thank you.
Can you check mine? Yeah. Big force, tiny acceleration, big speed, tiny speed.
That's still the one.
Yeah, I think this one's backwards somehow. But the concepts here are good. And we can look at this one in a second. Let me just shut my camera off so I'm not recording dead air.